Welcome to section 9.5. Probably wondering why is 9.5 coming after 10.2? Well, when I was in chapter 9 and I was breaking this all down, they were doing combinations in chapter 9 and they define combinations in section 10.2, which I thought was very strange. So I kind of put this in the right order. And what the author was doing, he was using Pascal's triangle to describe that combination notation that has the parentheses and it has the n over the r. It looks like a fraction inside of the parentheses with no fraction bar. And again, I'll point that out to you in this section as well. But here is what we're going to use: Pascal's triangle and the binomial expansion theorem. Very powerful stuff. All right, so Pascal's triangle, which is really not his triangle, this was actually discovered in China. It's just that the mathematician, Mr. Pascal, happened to be traveling through China, saw it, took notes, and published it himself. All right, back in the early days, China didn't publish anything. So, Pascal's triangle, you have to have ones on the corners. All right, then what we're going to do next is you're going to add these two numbers together. That sum will be a 2, and you're going to put it right down in between the numbers, and again put ones on the corners. So now this will go from row 0 to row 1 to row 2. Now, how do I know what row number I'm in? It's always the second number in. Top row 0, there's no second number, so that's a 0. Row 1, second number 1. Row 2, second number 2. If I want to build the next row, now we add the 1 and the 2, and we'll put 3's at the bottom and put in our 1's, and then there's row 3. And we can keep doing this addition and build more rows of Pascal's triangle. All right, well, what the author wanted you to do is build these rows all the time. And he would ask you questions and combinations where you'd have to go to build more rows. So no, we're not going to do that. We're not going to waste our time. So the theory here is that all these numbers in red are technically combination numbers. So looking at row 6, all right, row 6 is 1, 6, 15, 20, 15, 6, and 1. 1 is in diagonal 0. That's the uphill diagonal. Diagonal 1 is the second diagonal, 2, 3, 4, 5, and 6. The reason we number those diagonals and we number these rows is if you want, this is the N for combinations. These numbers down here are the R. So this one right here is 6 combination 0. This 6 is 6 combination 1. 15 is 6 combination 2. 20 is 6 combination 3. 6 combination 4. 6 combination 5. And finally 6 combination 6. And one of the things you should notice about these rows is that they're ascending and descending. That means they count up until they get to the midpoint, and then they count backwards from where they've already been at. Which kind of makes sense, because if you think of the combination definition, you have n minus r times the extra r factorial. So for 6 combination 2, I'd have 6 factorial on the top, 4 factorial times 2 factorial. Okay, and then when it's 4, 6 minus 4 is 2 factorial first, then 4 factorial. It's the same as this. 6 combination 2 is the same as 6 combination 4. So if you have an even row number, you shall have one more term than the row. So there's 7 numbers here, so there's one distinct middle number. But like in row 5, we have 2 10s because there is technically no middle number. Row 4, distinct middle number. Row 3, nothing, so the numbers repeat in the middle. Okay? Now, what I was mentioning earlier, this is when you'll see in this section, probably in View an Example, you're going to see this notation for the combination 6 over 5. So this is 6 combination 5, but I'm always going to use this notation so we know what we're talking about. Okay? Now, the one thing I notice here in row 6 is the n stays the same, but your r value keeps changing by the sequence of integers. Oh, I just gave it away. A sequence of integers. So you can build any row in Pascal's triangle without having to start at the top and work your way down. Because think of it this way. If you accidentally added something wrong, that number here added to these numbers generate more numbers. So then you get this triangle of wrong numbers. So if I made a mistake here at 3 plus 3, I don't know, called it 5, 9, whatever, some wrong number, then that mistake travels the rest of the way down. So how we're going to do this in our calculator to find the 5th row and have the calculator generate that row, we use a sequence command. So we're going to put this in our calculator. We're going to go to the sequence command, which is, I believe, second stat, going over to ops number 5. We're going to type in 5 combination x, because that's always changing. 0, 1, 2, 3, 4, 5, 6. You got to tell the calculator what variable you're changing. You got to tell the calculator where to start, where to end. And in the newer calculators, you got to tell the calculator what to count by. So in the older calculators, this is how it's going to be entered if you don't get that little pop-up sequence window. And you hit enter, it gives you all the numbers. All right, if it's the new calculator, let me bring mine in here. So it's going to be second stat ops number 5. That's my sequence command. But they give me this little window. So I'm going to type in 5. That's my n. Math, go over to probability, choose the combination number 3, x, that's my sequence function. What's the variable? X, enter. Where do I start? 0, enter. Where do I end? 5. These two have to match. And again, the step is what do we count by? We'll just say 1, enter. Paste it into the home screen. So again, the only thing different is we get this extra 1 on the newer calculators. But if I hit enter, there's my 5th row of Pascal's triangle. All right. Okay. Now, when I was introduced to Pascal's triangle was in college, and my college algebra teacher thought that we already knew Pascal's triangle. Well, I didn't know what it was. All right, so this is how I was introduced to it. So I was in class, and I'll admit it, I was pretty arrogant. I thought I could do everything really fast in math because I was always good in junior high and high school. But then when you get to college, it's a whole new experience. And I had a professor that said, oh, now, okay, we need to evaluate x plus 1 to the 5th power. And out of the blue, he just starts writing down x to the 5th plus 5, x to the 4th plus 10x cubed plus 10x squared plus 5x plus 1. And I'm sitting in the front row. My jaw is on the desk going, because I'm trying to FOIL this all out. I'm going x plus 1, x plus 1, and multiplying it all out. And I'm going x squared plus 2x plus 1. Okay, and I'm going to have to multiply that by... And I'm trying to... How in the world did he do this so fast? So, of course, I had to bother him and say, okay, how did you know that? He goes, I just used Pascal's triangle. I said, what? He goes, look at the numbers. This is 1, 5, 10, 10, 5, 1. I'm using what is known as the binomial expansion theorem, which uses combination numbers. And it's really easy to use that when, of course, you have 1s in the binomial, because 1 times anything doesn't change it. So all my coefficient numbers are going to be Pascal's row numbers, and then the powers have to go in descending order all the way to x to the 0. By the way, there's your diagonal numbers, or your R numbers, 5, 4, 3, 2, 1, 0. They're in descending order. So that's our next stop. We're going to go talk about the binomial expansion theorem. So again, you might see this n over r in that combination spot in this section. I don't like that notation. I'm always going to use the NCR. I will always use capital C. But this is a summation because we're adding all the terms together. So if I had x plus y to the n power, the n goes on the top, r starts at 0, and your combination numbers, this is going to be your row numbers out of Pascal's triangle. You're going to multiply it by this first term to the n minus r. This is your decreasing power times your second term raised to the r, which is your increasing power. So all these terms, there's the numbers of Pascal's triangle. Then we're going to evaluate x to the n times y to the 0. X to the n minus 1 times y to the first. X to the n minus 2 times y squared, until you get to where the n and the r are the same. You'll have x to the 0 power, and your second term will be raised to the n power. All right? So if I wanted to expand 2x minus 3y to the 4th power, the 4 is going in for all my n's, which means I want the 4th row of Pascal's triangle. So if you look back real quick, it's 1, 4, 6, 4, 1. I'm going to put these into my formula. Okay? All right, next, I'm going to take and put colored parentheses around my x terms and my y terms. Now, if you don't have colored pencils or pens, do parentheses and brackets. All right? So I'm going to start to write this out as my first number in the 4th row of Pascal's triangle will be 1. Then the first term to the 4th power, second term to the 0 power, plus 4, red parentheses to the 3rd power, second parentheses or brackets to the 1st power for the second term. Then plus 6, red parentheses to the 2nd, blue to the 2nd. First term decreasing, second term increasing. Plus 4, first term to the 1st, second term to the 3rd. Plus 1, first term to the 0, second term to the 4th. And then what we're going to do is, okay, the 2x, that's my first term. I'm going to put 2x in every set of red parentheses. Please make sure you understand how to do this, because this is how you show your work on the test. I will ask you to do this by the binomial expansion theorem. You can't sit here and FOIL this out. Okay? Next, we're going to take the minus 3. It's a plus in the formula, so this would be plus a negative. So that sign goes with the 3. So negative 3y in all the blue parentheses. So that's my setup. Once you show me this, now you can have your calculator crunch this out if you want. So 1 times 2 to the 4th. Oh, this is great. Negative 3y to the 0, that's just a 1. You can cross this out. So if you want to cross this out here and over here, because they're just a 1. So 2 to the 4th is 16, x to the 4th, 16x to the 4th. Now I'm just going to put this y to the 0 here just to hammer home the point when we're done. All right, next we're going to have 4 times 2 to the 3rd. 2 to the 3rd is 8. 8 times 4 is 32. 32 times negative 3 to the 1st is just negative 3. That's negative 96 x to the 3rd, y to the 1st. Then plus, let's see, 2 squared is 4. Negative 3 squared is 9, so 6 times 4 times 9. If you need your calculator, go get your calculator. All right, so that, I believe, is 216 x squared y squared. Then we're going to have 4 times 2 to the first, negative 3 to the third power, well, that's negative 27. Negative 27 times this 8 is a negative 216 x to the first, y to the third. Like we said, we cross this out because that's a 1. So negative 3 to the fourth power is 81 y to the fourth. But again, I'm keeping that x to the 0 power here to notice something special about your powers. All the exponents on your variables have to add up to 4, which is the power on your binomial. So my first term, x's, powers are descending until it's a 0, which we really don't write down. And in the second term, powers are ascending from 0, which you really don't write down. But then the next term is 1, 2, 3, 4 for the powers, and that's my final answer. Right there. So instead of doing all that foiling craziness, we outline the work by the definition, plug in the terms in each set of parentheses or brackets, if you want to do one of each. If you can't, don't color code it. And then crunch the numbers individually, and you got your answers. All right? Now, again, Pascal's triangle, very helpful when you're going to see this question. Find the coefficient of x to the 7th power of 2x minus 3 raised to the 10th power. All right? So, if you remember back to our previous example, the x powers are descending. The y's are increasing. And they have to add up to be the same thing. So this is going to be x to the 7th. So this term to the 7th power, this term to the 3rd power, and your n is 10. So the 7 subtracted from the 10 gives me the 3, or you can remember that these two terms have to have their powers add up. So I'm going to write down, based on my formula, n is 10, 10 combination 3, all right, times x to the 7th power, because they already gave me the 7 on the power of x. And then the second term, minus 3, to the 3 power. So all of 2x is going to be raised to the 7th power. Negative 3 is raised to the 3rd power. So to go crunch this out, 10 to the 3rd, I'll just do that in my calculator, that's 120. 2 to the 7th is 128 times your x to the 7th. And we saw earlier that negative 3 to the 3rd was negative 27. Multiply all those numbers together, and you get the coefficient as negative 414,720 x to the 7th power. There's my coefficient. Now, please make sure you understand this formula, because there will probably be a question like this on the test, something similar to it, okay? And I asked something like this, very similar numbers, and someone forgot the formula but wanted to find the coefficient, and they literally wrote this out 10 times and foiled the whole thing together as their work. Yep, I kid you not. Fortunately, they got it right. They did not make any arithmetic errors in all that foiling. Now, the second example here, it looks similar to the first. It says find the 7th term. Okay, now that's the 7th term counting backwards on my x's. So what I'm going to do here to find the appropriate r value is, remember, your r has to start counting at 0. And I count up to 10. Now, that's important because that's the 0 on the second term. If we counted a y like we did earlier, that's y to the 0, y to the first, y to the third. This is telling us our terms. So you count first term, second term, third, fourth, fifth, sixth, seventh term. 1, 2, 3, 4, 5, 6, 7. So R is going to be 6 on my seventh term. Well, that means that's negative 3 to the sixth power. This is going to be 2x all to the fourth power, because remember the two powers have to add up to be 10. So we're going to go 10 combination 6, the 2x to the fourth power times the negative 3 to the sixth power. All right, well, 10 to the sixth is 210. 2 to the fourth is 16. So that's 16x to the fourth, and negative 3 to the sixth power is 729. Multiply those three numbers together, 2,449,440 x squared. That's the seventh term of that expanded binomial. Okay? So again, get used to working with this formula. Guaranteed you'll see something on the test. And I promise you, this is on the test right here. And it will specifically say, use the binomial expansion theorem, show your outline work to find the answer. So you have to show this part as your work. Once that's written out, you can use whatever you want, your calculator, to crunch the numbers and the variables. Okay? All right, so we'll